Here we go with Unit 2. Again, we're going to do this in 4 sessions. This first session, we'll define the 6 trig functions. We'll use right triangles to do that. Then we are going to take a given point somewhere on the coordinate plane. We're going to say that that point lies on the terminal side. Oops, I kind of missed it, didn't I? Lies on the terminal side of that angle. And just knowing what this point is, we can figure out the value of the 6 trig functions. In the following sections that we'll do in the next 3 after this, we will deal with this piece of it. So today it's basically defining these 6 trig functions. You probably have heard of this famous chieftain, Sokotoa. Yes? Well, if any of you have dealt with Mr. Schaff, he always, I think, introduced his geometry students to Sokotoa. It's actually just a helpful way of remembering what the 3 basic trig functions are. Sine, this is sine right here, cosine, ka, and T for tangent. Those are, if you remember these 3, you'll be in good shape. Now, what are we trying to remember? Well, for sine, if we have any angle and we find its sine, that will be, in a right triangle, the opposite side, that length, divided by the hypotenuse. So we say sine of theta equals opposite divided by hypotenuse. Sine of theta is opposite divided by hypotenuse. So cosine of theta is the length of the adjacent side divided by the hypotenuse. So for cosine we get ka, adjacent hypotenuse. And then for tangent, this one doesn't deal with the hypotenuse. Tangent just deals with the ratio between the opposite side and the adjacent side. That's where we get toa, opposite, adjacent. So, katoa. Remember that and it will help you get these straight. The function sine theta has as its input the angle measure, and there are 2 ways we can measure angles. Remember that? We can measure them in degrees or we can measure them in radians. And we can do that with the trig functions. We can measure in either degrees or radians. It's important to know which we're doing. Sine theta, the ratio of the opposite divided by the hypotenuse, is the output. This is the way we read all the functions. Just like function f of x, where x is the input, now you're reading sine of theta, where theta is the input. Cosine theta, theta is the input. Tangent theta, theta is the input. The output is one of these ratios, and you're going to be able to remember which one this way. This will get you started. The other 3 ratios, sine has a reciprocal ratio called cosecant, which is just the reciprocal of sine. Instead of being opposite over hypotenuse, it's hypotenuse over opposite. Cosine, its reciprocal is secant. instead of adjacent over hypotenuse, the ka, it's now the hypotenuse over the adjacent. Please notice, this tricked me when I was in high school. I couldn't figure it out for the longest time. Sine is associated with cosecant. Cosine is associated with secant. When you look at these reciprocals, all of them, only one is a co. So when you think about these reciprocals, if you've already got the co and cosine, then its reciprocal is secant. You notice here with tangent, cotangent, the reciprocal of tangent. So those are your 6 functions. If we put these into standard position, opposite over hypotenuse, if we take, let's see if I can move this. I can't remove, oops, that's no good. Let's see if I can move that. I can. So if we took this and we put it right here, you can see that what was the hypotenuse in the case of a circle here becomes a radius. What was adjacent becomes x, and what was opposite becomes y. So these can be redefined. Instead of opposite over hypotenuse, you can say the vertical y divided by, instead of hypotenuse, the radius. So if you place these into a coordinate plane, the point on the terminal side of this angle, which lies on the circle, that point is x and y, where x represents the adjacent and y represents the opposite. Okay, so all of these can be defined with x's and y's if they are located on a coordinate plane in standard position. You remember standard position is when theta, its vertex, is right at the origin. What Greek mathematician, you know this one, comes to mind when you think about a right triangle? Pythagoras, right? Of course. How many times have you used this particular formula, the Pythagorean theorem? If you square, with the right triangle, if you square the two legs, square this one, add it to the square of this one, it will equal the hypotenuse squared. If we think about this in terms of a triangle where this is in standard position, sorry about my poor drawing. If you think about this as a right triangle with the vertex in standard position, then you can see x squared, y squared, and r squared. Thinking about this as a circle, right? Oh boy, I'm bad enough at straight lines, and you can see I'm not doing well at all with circles, and I don't know why that little message pops up. I suppose I should find out, huh? Okay, so Pythagoras becomes very important to us in trigonometry. I'll show you some examples of this coming up. Each of the 6 trig functions can be paired to another that is its reciprocal. Find the 3 pairs of reciprocals. Well, we don't have to go very far. I'm not even going to write anything down. Whoops! Because they're right here, aren't they? Sine, its reciprocal, cosecant. I didn't even mention the abbreviations we use for these. This is sine, pronounced sine, not sin. We just use 3 letters to designate sine, 3 letters to designate cosecant. Then the reciprocal partners here are cosine and secant. Reciprocal partners here, tangent and cotangent. Which trig function can be written as the quotient sine theta over cosine theta? So we have 6 of them, right? Which one can be written this way? Well, I'm going to back up a moment. Let's think about sine theta as y over r, that ratio, and cosine theta as x over r. And so let's write it that way. So this would equal y over r and x over r. Since we have 1 over r in the numerator and 1 over r in the denominator, we could simplify this, right? To y over x. Let's go back a moment. Which of these is written as, here it is, y over x? So the answer is tangent theta. It could be written as the quotient sine theta divided by cosine theta. We're going to spend so much time looking at the relationships between these, so start to get used to it. Which trig function can be written as this quotient? Ooh, now this one looks a little more complicated to me, but let's try it out. Cosecant theta and cotangent theta. Let's see what they look like over here. Cosecant theta and cotangent theta. Okay, let's write those out. Cosecant theta is r over y. Cotangent theta is x over y. So we have a similar situation as we had here, only this time it's y that's common to both the numerator and the denominator. So that will simplify to r over x. If it were x over r, it would be cosine theta, but it's the reciprocal of that, so it must be secant theta. Let's check that out. Secant theta r over x. What is a simplified product of all 6 trig functions multiplied together? So, wow. So we'll start with sine. And what's its reciprocal? Now you can already see what's going to happen. Because when you put in those 3 basic ones, and then you multiply the reciprocal, what's going to happen? So I'm writing out all 6 ratios. And you can see what's going to happen there. Y over y is 1. R over r is 1. X over x is 1. R over r is 1. 1, 1, 1, 1. All those ones, multiply them together, you have 1. Pretty neat. Okay, the 5th question here might be a little trickier. I do have a hint ready if anybody wants to see it. Which two trig functions, so there's two of them, must be less than 1 for any acute angle theta? So if we're looking in this first quadrant, right, between 0 and 90 degrees, we have an acute angle. Which two must be less than 1? All right, let's look at the hint. Some of you have already got it. Here's the hint. What is always the longest side of a right triangle? That's right, you learned this back in geometry. The hypotenuse is always the longest side of a right triangle. So let's look at these functions. When we place this on a coordinate plane and think about this as a unit circle, the radius represents the hypotenuse. This is the longest side. So y will never be greater than r, will it? X will never be greater than r. With these two, you don't know. This certainly could be greater than 1. This one is definitely going to be greater than 1, isn't it? Certainly never going to be less than 1 because r is the bigger, typically the bigger number. It's y is never larger than r, x is never larger than this, and this could be anything. So our answer here is sine and cosine. Those never get to be greater than 1. So must be less than 1 cosine theta and sine theta. We just dealt with a lot of conceptual stuff related to trig functions. I hope that was fun for you. This comes right out of your workbook. When you're defining trig functions, this is so important. There's no such thing as sine. Well, it can't exist all by itself. It's sine as defined by some angle. Sine theta, sine alpha, sine x, something here to determine what the angle is. Every trig function is a function of an angle. You know, it's surprising how many people forget that, because many times I have students who will write something like this: sine equals, and they'll give me a number. No, there is no such thing as sine. What's missing here? The angle. Do not write any of these trig functions without putting in some representation for the angle. We know that an angle has to be there, but that's not an excuse for not putting in a representation. Let P be a point on the terminal side of theta. Draw a picture. Ooh, that's such a good idea. I am going to be counseling you to draw pictures, not only in trig, but also next semester in stats. If I assume that this each grid is 1 by 1, my point 3 somewhere here, and 4, so where do those meet? Right there. Draw a picture. All right, I'm going to draw a picture for sure. This is a right triangle. My x is equal to 3. My y is equal to 4, and I'm going to use the Pythagorean theorem to figure out what my r is. How do I do that? I say 3 squared, which is 9, plus 4 squared, 16. Add them together. 9 plus 16 gives me 25. And I take the square root of that. Now, many of you are already familiar with this. You would know immediately. This is a 3, 4, 5 triangle. It's one of the Pythagorean triplets. So what are the 6 trig functions then? Well, we've got sine, theta. This is our theta right here. Sine theta is y over r, so 4/5. You can write it just like this, a little fraction. Cosine theta is 3, that's our x, over 5. And tangent theta is y over x, it's 4/3. Now notice here, just as we had said earlier, sine is less than 1, cosine is less than 1. Can never be greater than 1, but look at tangent. No problem with it being greater than 1. And then we want to do our reciprocals. I advise you to do sine, cosine, tangent. Get those done, because then the reciprocals are quite simple. Remember, if you've got sine, its reciprocal partner is going to have the co in it. So that's cosecant theta. And you just write the reciprocal. And cosine already has the co in it, so its reciprocal partner is secant. Tangent, its reciprocal partner is cotangent. Okay? Now I think you could do all of these. Let's go down to f. The square root of 2. Now if I'm going to graph this, I kind of need to know what the square root of 2 is in decimal. I probably should know it by heart. I'm going to take the square root of 2, which is equal to, so this point, I'm just going to re-express it as a decimal, say 1.4, because when I go to graph this, the square root of 2 doesn't help me. I need to know what its decimal is. And then the other one I want to know is square root of 7. Okay, 2.6. Now for figuring the trig function, I'm not going to use the decimals, I'm going to use the exacts. But because I'm trying to graph, I want to have an idea where this is. Okay, so I've got 1.4 somewhere along here. And I've got 2.6, which is somewhere along here. So this point, right about there, with my x being the square root of 2, my y being the square root of 7, and my r being, what do I do? Square this, it becomes 2. Square this, it becomes 7. Add them together. Square root of 9, which is 3. So sine theta is the square root of 7 over 3. cosine theta is the square root of 2, my x value, over 3. And tangent theta is square root of 7 over the square root of 2. Please never express these answers in decimal. The only reason I'm using decimal at all was so that I could graph. But as far as finding the trig functions, be exact. We will violate that rule later on. We'll use decimal approximations. But right now, I want you to be exact. Quadrants in which functions are positive. All functions are positive in the first quadrant. What happens to sine when we get into the second quadrant? It's still positive, isn't it? X becomes negative, but y, r is always positive. But x becomes negative, but y is still positive. So these are positive in the first quadrant and the second quadrant. When I get down here into the third and fourth quadrant, y is negative, and both of these are negative. They're reciprocal partners. Cosine, on the other hand, although it's positive in the first, it goes negative in the second quadrant, and it is still negative in the third quadrant. It goes positive again in the fourth quadrant. Tangent is probably the most interesting because it has both x and y. So you have to look at what they do together. X and y are both positive in the first quadrant. X and y are both negative in the third quadrant. And they have opposite signs, keeping the ratio negative in the second and third quadrant. There is a way to remember these. Think about it this way: the first quadrant, second quadrant, third quadrant, and fourth quadrant. Remember, we always go counterclockwise as we count these. All are positive in the first. Sine and its reciprocal in the second. Tangent and its reciprocal in the third. Cosine and its reciprocal in the fourth. You might want to remember it this way: all St. Thomas cousins. Would that help? All St. Thomas cousins, when you try to remember which are which. Of course, you can figure it out for yourself, but time is usually too valuable to try and figure everything out from scratch. Before we end today, we're going to spend a little bit of time talking about what a reference angle is. A reference angle is the acute angle between whatever the terminal side is of the angle and the horizontal axis. For example, the reference angle for 120 degrees, here it is, or a negative 240, remember that would be coterminal, or 480, we go around 360 and then another 120. All of these have the same reference angle. It's the acute angle, which is this one, isn't it? This is the acute angle. Acute angle, which is 60 degrees. So all these coterminal angles have the same reference angle. The important thing to remember is it's the acute angle between the terminal side and the x-axis. So for 259 degrees, find the measure of the reference angle. Okay? Well, this would take me to 90, 180. If I went all the way over here, it would be 270. So I'm not going to go all that way. I think each of these are 15 degrees, aren't they? Let me think about that for a minute. This is 45. Yeah, each of these are 15 degrees. So if I cut it out, if I add another 30 degrees, what am I up to now? 210. Another 30 degrees. 240. Over here would be 270. I don't go quite that far, do I? So I go right to about here. So there's my terrible drawing, isn't it? But that's 259 degrees. 259 degrees. Now, let me use a different color. Where is our reference angle? Well, what is a reference angle again? It's the acute angle formed by the terminal side, which is right here, and the horizontal. So this can't be it, because that's not acute, that's obtuse. Here is my reference angle. And what is my reference angle? Well, 259 is this whole angle, and this 180 is what I have to subtract from it. So I'm going to say 259, and I'll subtract the 180, and that will give me my reference angle, won't it? 79 degrees is my reference angle. Okay. Oh, yeah, let's think about radians. We haven't talked about them at all in this session. Just at the beginning saying that they existed, right? So we could be measuring our angles in radians. So let's see, what would this be? 2 pi divided by 5. Well, 2 pi, if it weren't divided by anything, would be a full circle, wouldn't it? 1 pi takes me here. Ugh, yikes. So if this is being divided by 5, 2 pi divided by 5, 2/5 of pi. That's another way I could think about it, right? I could think about it this way. 2/5 of pi. And I know pi is a semicircle. So 1/5 of pi would take me to here, wouldn't it? Is that true? No, it's not. Let me, 5, I'm going to divide it into 180. I think so much better in degrees than I do in radians. I usually find myself making the conversion back and forth. It's like not being fluent in a language. 36 degrees is 1/5 of pi. So I want to go to 72 degrees. All right. So, I don't know, right about there. So, find the measure of the reference angle here. I'm looking for the acute angle formed by the terminal side and the x-axis. Turns out it's exactly the same, right? It's 2 pi over 5. That's my reference angle. Makes me think back here. I don't think I marked this. This would be my reference angle. Oh, you notice reference angles are not paying any attention at all to what quadrant they are in. That's where you have to pay a lot of attention to all St. Thomas cousins, to know that if your angle is over here, to know which of your trig functions are going to be positive. All the others are going to be negative. Previously, when we did this exercise, we were looking at only one quadrant. Let me move back there for a moment. Right here, we're just looking at the first quadrant. But now, with the introduction of how we interpret each of these trig functions sign-wise in each of these quadrants, and the introduction of the reference angle, we can work in any quadrant we like. So let's try that. I'm going to start out with this one. Now, -8, I can't define this as a 1-by-1 grid. That won't work. But if I did it as a 2-by-2, it would. So just doing this will inform my reader that I'm using a 2-by-2. So -8 for my x takes me over here, and a +6, so I end up right here. Make it a big dot, I guess. And my angle, my theta in standard position is right here, isn't it? This is my theta. I don't have to know what theta is as long as I know what this point is, and I do. Let me draw the triangle that's associated with it in a different color. So we've got, oh, that's terrible. I have to redo it. There's my y, there's my x, and there's my r, right? So I've got an x, which is -8, a y, which is a +6, and an r, which I have to figure out. You may recognize that this is just a multiple of the 3, 4, 5 triangle. And we could use the Pythagorean theorem to figure that out as well. Square this, add them together. You get 100, you take the square root of 100 of 10. So, sine of theta. What is it going to be in the second quadrant? We know that in the second quadrant it is still positive. It's defined as y divided by r, which is 6 divided by 10. 6 divided by 10 will simplify to a +3/5. Cosine, what do we expect cosine to be in the second quadrant? We expect that to be negative, and it is. It's -8 over 10, x over r, which simplifies to -4/5. And then we have cotangent. Oh, what am I saying? We don't have cotangent. We'll get cotangent in a minute. We should do sine, cosine, and tangent first. And that's y, a 6, over x, or a -3/4. True? 3 over a negative 8 will simplify to a negative 3/4. The reciprocals, the reciprocal partner for sine has the co in it. It's cosecant. Cosecant theta is 5/3. Notice how sine is never greater than 1, but this sure is. And then the reciprocal partner for cosine, it's already got the co here, so this one is secant theta. And that is negative. It's a negative. It's the reciprocal of this, which is negative 5/4. Tangent theta, its reciprocal partner is cotangent theta. Notice that reciprocal partners always have the same sign as each other. (4/3), negative 4/3. I'm going to skip right down here to this one. In the interest of time here, you can do these other two, and I recommend that you do. I'm going to look for those in your notebooks, in your workbooks. The point that we've got here, that can be located in this as a 1-by-1 grid. Let me bring this over so I can figure out what is the decimal equivalent of the square root of 3. 1.7. Okay? So when I go to plot this, it's going to be negative 1 and a positive 1.7. So a negative 1 takes me here, a positive 1.7 takes me right about there, right? So I have this is my theta. Well, this maybe was a bad example because it's so similar to the one we just did. Oh, just want to make that point a little more conspicuous. Oop, that's more conspicuous for sure. Then we could figure out what x is, right? X, we know is negative 1. That's given to us. Y is a positive square root of 3. And R, what's that going to equal? We square this, we get a positive 1. We square this, we have a positive 3. Add them together, positive 4. We take the square root of that. And our radius right here, let me draw that triangle in. This is our reference angle right here, this one here. Draw the triangle that goes with it. Oh, terrible. Okay, so my radius is 2, my y is 1.7 or square root of 3, and my x is negative 1. Sine of theta, in the second quadrant we know it's positive. It's going to be the square root of 3y over the radius 2. Cosine theta equals negative 1 over 2. And tangent theta equals negative square root of 3. Now I know I probably could have written this as a fraction, right? Positive square root of 3 divided by negative 1, but that's going to simplify to this. Then when I do the reciprocal partners, I get cosecant theta is a positive 2 over the square root of 3. The reciprocal partner of cosine is secant theta and that's going to simplify to a -2. And the reciprocal partner of tangent is cotangent theta, and that's going to be -1 over the square root of 3. Something I should point out about this triangle, let me draw it a little larger, because I think, oh, I have got to improve my drawing skills. Okay, straight lines. It should be pretty simple. I'm going to try and draw it here. Okay, this is a right angle. And we said this was actually a -1. I'm just going to put a 1 there. This was the square root of 3, and this was 2. Do these look familiar to you? They should. They should look familiar to you. This is a famous triangle. This is the 30, 60, 90 triangle. Remember that one? Where the ratio of the sides is 1 square root of 3 and 2 for the hypotenuse. You know 2 has to be the hypotenuse because it is the longest measure, right? This is only equivalent to 1.7. Couldn't possibly be the hypotenuse. You have to have the longest as the hypotenuse. Okay, that's it. It was a fairly long lesson. I will see you in class. If you didn't get to finish all the examples yet, we can finish those in class along with this homework.